there are some atoms that become more stable by losing just one electron, like sodium and all the other elements in that alkali metal family. But there are other atoms that might need to lose more than one electron in order to get a full outer shell. We call that successive ionization energies. It refers to like how much energy is required to remove the first electron, how much energy is required to remove the second or the third or the fourth electron. So when they've got this chart here and it's got like I1, I2, I3, I4, like if you see I4 is the amount of energy needed to remove the fourth electron. Energy to remove the fourth electron. That's kind of what it refers to as successive ionization energies. How much energy does it take to remove the first, the second, the third, the fourth, and so on? Okay, so they give us this little chart here that's got measured numbers for successive ionization energies in units of kilojoules per mole, which isn't really a concern for us. I just want to look for trends and patterns. And there are two things that concern me about this little graph. Number one, I'm not sure why it's not like this, but you might want to like extend this black staircase. So you know the staircase in here, this dark black, it should kind of go like this too. There. It should go up to sodium as well. I'm not sure why it wasn't, but you could do that if you want to. Okay, so two things that I want to look at. Number one, I want to know why there is that staircase in there. And I want to know, like for a particular element, it always seems to increase. So like if I'm looking at silicone, it takes about 786 kilojoules to remove the first electron, then 1,577 kilojoules to remove the second, then over 3,000 kilojoules for the third, over 4,000 kilojoules for the fourth, and then, geez, it jumps from 4,000 to like 16,000, almost 17,000 kilojoules to remove the fifth. So I want to know, like, why do they increase? Why does it always take more energy to remove the electrons? Especially when I think about like the arrangement of the electrons in an atom. So for example, what if we pick on our friend sodium? Sodium's electron configuration is given to us, but I kind of like to also think about the orbital diagram. So if I were to write sodium's orbital diagram, I'd have the 1s and the 2s, and then I'd have maybe like the 2p orbitals. They're all equal energy, and then the 3s. Sodium is element number 11, so I would fill 1, 2, 3, 4, 5, 6, 7. I gotta pair them for 8, 9, 10, and 11. Okay, so we've said that in order to fill the outer shell, sodium would like to lose that outer electron. And so this ionization energy is the amount of energy it takes to remove the outermost electron, and the goal then is to have a full outer shell. So in sodium, for example, these are going to be my core electrons. And this guy in the 3s is my valence. And we said, you know, the goal is to lose electrons to a point where I have a full outer shell. So right now I've got one valence electron, and sodium would like to lose that one, because then I'm just down to all my core electrons. And my core electrons are the stable electrons that are in nice full orbitals. And I've got a full energy level then. My outermost level, if I get rid of this guy, then my outer level is the second, and the second has all full orbitals. or 8 valence electrons. We call it the Octet Rule, where atoms tend to be most stable when they have 8 valence electrons. And it just comes from the fact that there would be 2 in the outermost s and 6 in the outermost p. Okay, so that's what sodium is trying to do. We try to lose that last electron. So for sodium, it's going to take 496 kilojoules to remove the outermost electron. But then look what happens when I try to lose the second electron of sodium. Holy buckets. Do you see right here? It jumps like almost tenfold. Whoa. Why would it take so much more energy to remove the second electron? So the first electron's like 500-ish kilojoules. Okay, cool. That would be the 3s. But then it goes up by like tenfold when I switch to now the second ionization energy. I2 would just mean removing the second electron. Do you kind of see why there's such a big jump? I don't want to lose 2 electrons. This is happiness right here. This is what we want. We want full orbitals and an outer energy level that's full. The second energy level is full. That would be like this here is my second energy level. And now it's full with 8 valence electrons. This is happiness. This is stability. When sodium has lost that 1 electron to form the sodium plus 1 ion. And I think sometimes people have a misconception and they think that like, ions have a charge. That charge seems kind of weird. That must mean unstable. It's actually the opposite. Forming a charged ion is often a good thing. Sodium atoms are crazy reactive because they only have 1 valence electron, and all they have to do is get rid of that 1, and then it's happiness. Then it's stability. Then the sodium plus 1 ion has all full orbitals and a nice full outer energy level. It's just that now the outer level is the second. And they kind of show that in a Bohr model down below this table, where we're going to add 496 kilojoules to remove that outer electron. But then when I get here, this is stable. I think somewhere I can maybe put like shapes in here. Oh, I wonder if there's a heart. Nope, there wasn't. I think there used to be one. This is like happiness. Oops, I'm putting birds on. But watch what it does. It makes little birds. Ha! I don't want that. It's putting little birds everywhere. I'll put a little red heart. This is happiness. When sodium has a full outer shell, the second outer shell is full now. Why would I want to lose another electron? I don't want to lose more, because now that would mean that I'm losing my core electrons, the stable electrons. We don't want to do that. So then it takes a ton of energy when you switch between losing valence electrons and core electrons. It's not stable to lose the core electrons. They're full. Oh, interesting. Okay, now let's look at magnesium. Let's look at magnesium. And so magnesium, Mg, would be really similar, right? 1s, 2s, and then I'd have my bloopy-doo, my 2p orbital, and then I'd end with my 3s. I mean, really similar. Magnesium just has 1 extra electron for 12. So I would have, I was doing those moves, 1s, 2, 2s, 2. I know I'm going to fill these p orbitals with 6, right? I mean, this only gets me to 10. And so then I'd need 11, 12. Okay, so my valence electrons are all the electrons in the highest energy level. So this 3s2, that's my valence. And my core electrons are all of the inner full orbitals. Here's my core. Okay, so a couple things. Number one, we're going to form a +2 ion. Magnesium has 2 electrons in the outer shell, but rather than try to gain 6 to fill the shell, because I didn't write them, but there would then be the 1, 2, 3. There would be the 3p orbitals, and they're empty. So I have to either gain 6 more electrons to have an outer shell that's full with 8, an octet, or I could just lose those 3s2 electrons. And in the end, it's way more stable just to lose these 2. It takes less commotion. Let's just lose 2 rather than find 6. So you're going to lose those 2 electrons. Now, when we lose those 2 electrons, here's what we have left. Let's write some comparisons. The neutral atom, so magnesium atom, when it's neutral, would have 12 protons and 12 electrons. Overall charge, 0. No charge, neutral. Well, then you remove 1 electron at a time. So next I would form the magnesium +1 ion. Well, first I lose an electron, but not a proton. So there would be 12 protons. And the first electron lost would leave me at 11. Oh yeah, okay, I see it. There's still 1 extra proton. That's where we get the +1 charge from. Now magnesium would like to go 1 further and lose 2 electrons. So then I'd end up with the magnesium +2 ion, where I'm always going to have 12 protons, but I want to lose both of those electrons in the 3s, so now I'm down to 10. Okay, so yep, I look at the balance of charge between the protons and the electrons. There's 2 extra protons compared to the electrons. That's where I get the +2 charge from. This is the most stable form of magnesium, the magnesium +2 ion. That's its happy place, where we finally lost those 2 outer electrons, and now I'm just down to my core. Valence electrons are all full. Now the valence shell would be the second. 8 valence electrons, all the orbitals are full. Okay, well, one thing I want to look at, and you can kind of see it on this Bohr model diagram too. So they show removing the first electron takes 738 kilojoules. Removing the second electron takes about 1,451 kilojoules. Well, then they even show removing a third electron, and now that jumps to like almost 8,000, 7,733 kilojoules. Well, number one, why do they keep increasing? Why do they keep increasing? It's not the same amount of energy to remove all the electrons. Well, think about the magnitude of the charges, especially the nucleus versus the electron cloud. I mean, 12 protons and 12 electrons, they're attracted to each other, but it's like the 12 positive charges from the nucleus are evenly distributed in a 1-to-1 ratio amongst the 12 negative electrons. But now in the magnesium +1 ion, I've got 12 positive charges, but I only have to distribute that amongst 11 electrons. We say greater nuclear charge, where the nucleus becomes more positively charged than the electron cloud. Well, yeah, it's just more positive charge distributed amongst less electrons means like each electron gets more than 1 positive charge. It's a stronger attraction. And when you get to the +2 ion, and the nucleus has 12 positive charges, but they only have to hold on to 10 negative electrons. So again, it's just like more positive charge to distribute amongst less electrons. So each electron gets a bigger share of the nuclear charge, stronger attraction. I mean, I think about it like with little toddlers. I don't know, let's say you're going to take a bunch of toddlers to the zoo. Well, if you've got a 1-to-1 ratio, then, I mean, there could be 12 toddlers and 12 teachers. Okay, so the toddlers are attracted to their teacher, 1-to-1. But if I get to a point where there's 12 teachers but only 10 toddlers, do you see how you could keep a stronger hold on those 10 kids, those 10 little toddlers? Because now you've got 2 extra teachers. And so if one toddler gets a little crazy, you've got 2 extra teachers to reel them back in. Oh, I don't know if that helps or not. I don't know, it helps me. When I think about distributing the positive charge, yeah, now I've got more teachers than kids. And especially if they're little crazy kids, little crazy electrons, and they're bouncing all over the place, I want to have a stronger hold on those 10 kids. Well, yeah, now if I've got more teachers, they can watch those 10 kids more closely. 12 protons will have a stronger hold on only 10 electrons. More charge distributed amongst less electrons. So as the nuclear charge becomes greater than the charge on the electron cloud, it's a stronger attraction. That's important. So for all of these, you'll notice that going across, each electron removed always takes more and more and more energy. Successive ionization energies always increase for any element. I mean, even sodium is first electron is 500. The second electron is obviously a lot more. And aluminum, it goes from about 578, a little less than 2,000, a little less than 3,000, then whoa, 11,000. I mean, they always increase because you're never ever changing the charge on the nucleus. But as you lose electrons, I mean, when I get argon and I'm at its I7, that's losing its 7th electron. Yeah, I mean, by that time you've got way more protons than electrons, and it's a greater nuclear charge. Somewhere I'm going to write that. I love that term. So here, when I'm thinking about this magnesium ion, 12 protons versus only 10 electrons, greater nuclear charge. Exclamation point. Greater nuclear charge, meaning that the nucleus has become more positive than the electron cloud. It's just a stronger attraction. So it always takes more energy to remove each successive electron because the attraction becomes stronger between the nucleus and the electron cloud. Okay, so that's one thing that I want us to be able to explain. Why does the ionization energy increase each time you remove another electron? The other thing that I want to be able to explain is why along that little black staircase is there a significant jump in ionization energy. In magnesium, I go from removing the second electron, that's 1,451 kilojoules, and then removing the third is almost 8,000. Well, if you look at the orbital diagram or even this Bohr model, do you kind of see what would happen? Oh, I'm okay losing 2 electrons from sodium because now I've got my core electrons. I've got my stable full orbitals. But does magnesium want to lose a 3rd electron? Heck no! We don't want to lose a 3rd electron. That's one of the core. So you'll always notice this huge jump in ionization energy, and it's always the switch from valence electrons to core. I'm going to write that in the chart too. These are my valence electrons. These would be core. I don't want to lose the core electrons. That's the whole point of forming an ion, is that I'm trying to lose just the valence, because the core electrons are the ones that are nice and full and stable. And so think about aluminum. And you can look at his electron configuration here, and that neon would represent the 10 core electrons. I mean, that's the case with the sodium and magnesium and all of these. That here I've got the orbital diagram showing the arrows in the boxes. But if we shorten it up to the electron configuration, we can just use neon because then it's the core. And the valence electrons are whatever comes at the end. Aluminum has 3 valence electrons. But if we're trying to get a full shell, I would need to either lose those 3 or I need to find 5 more so I can fill the 3p orbital. Right now it's 3p1. I would want it to end 3p6. I want it full. Well, lose 3, gain 5. It's more stable to lose 3. So I'm okay losing 1 electron, losing 2 electrons, losing 3 electrons, but we don't want to lose 4. That's going to be one of the core electrons. I don't want to lose the 4th electron. We never want to lose the stable core. I think about like silicone. Silicone's got 4 valence electrons. We'll lose the 1st, the 2nd, the 3rd, the 4th. But then you see that giant gap? I mean, it goes from 4,356 kilojoules to lose the 4th valence electron. But to lose the 5th, now it's almost 17,000. That's the switch from valence to core. There's 4 valence electrons, but the 5th electron would be a core. And those are full, stable. We don't want to lose the core. So they're going to always take a ton of energy to remove. Rarely would that ever even happen. And so really then when you get to question 15, it says to draw a successive ionization energy diagram for aluminum. And so I don't know, I mean, you could draw it with a Bohr model, kind of like these Bohr models they did down with sodium and magnesium. You could have drawn orbital diagrams to show what happens when aluminum starts to lose electrons. And in a nutshell, it's just that the aluminum has its 3 valence electrons, and we're okay losing 1, losing 2, losing 3, but I don't want to lose the core. This one would be like, these are happy faces. This one gets a big sad face. Whoa. No, I don't want to lose the core. Those are the full stable orbitals. And we can also explain the general increase in just that, well, if I have the aluminum atom, the neutral aluminum atom is 13 protons and 13 electrons. Attraction. Well, then as I start to lose electrons, first I would form the +1 ion, where we always have 13 protons, but then I would only have 12 electrons. So it's just a higher charge distribution from the positive nucleus to the negative electron cloud. Then next I would lose the 2nd electron to form the +2 ion. We always keep 13 protons, but now I would only have 11 electrons. That's where the +2 charge comes in, right? The balance between the protons and the electrons. And then finally the aluminum +3 ion. 13 positive protons, but only 10 negative electrons. And again, this is going to take the most energy to remove electrons. This is my strongest attraction. It's my greatest nuclear charge. Now the nucleus is obviously always +13, but the charge here on the nucleus is way greater than the charge on the electron cloud. So when we say greater nuclear charge, we mean in comparison to the charge on the electron cloud. This then would be the strongest attraction. +13 positives that only have to distribute amongst 10 negatives. That's the strongest attraction. And so each time the attraction gets a little stronger and a little stronger, and that's why it takes more energy to remove each successive electron. But after losing 3, then the ionization energy goes crazy, because I don't want to lose the 4th core electron.